A computer chip is one of the most astounding feats of human engineering. We build computer chips in ultra-clean facilities that are called clean rooms, which are cleaner than a surgery room. And in order to build a chip, we start with a base that is called silicon wafer. And this is the purest material that we have on Earth today. And we take this silicon wafer and take it through layers of processing, something like layering a cake, fabricating a recipe in a kitchen. So we start by designing the chip and transferring that design into a mask set that we then use to pattern the features onto the wafer. After we have the features that we want, we take the wafer into adding material, a process that we call material deposition, or removing material depending on the step, a process that we call etching. Another step that we need to do is planarization, because we want the layers to be nice and flat as we build our computer chip. So we're going to design circuits that are going to be part of the test structures for the nanotechnology accelerator to test the emerging device technologies together with existing transistor devices for benchmarking purposes. And then the second aspect that we have been contributing is device integration, doing these novel devices and actually prototyping them on these chips and show proof of concept, developing documentation that other universities, other partners can then use for their own devices. My group at GW is actually the first university partner showing successful integration of our devices called memristors onto these 20,000 device platform. And a third aspect that is very important is workforce development. We have students working on these devices, on circuit design, so we're developing the pipeline for the next generation of workforce that is aware of interdisciplinary challenges and what it takes to build semiconductor chips. This partnership is extremely critical because it provides the research infrastructure needed to make advancements in the field of nanotechnology and semiconductor devices. This will enable different researchers who are using the same platform to test their novel devices that they fabricate in their own facilities and benchmark them against the community, because the other researchers are also going to use the same platform. And this is really powerful approach to benchmark new device technologies. And the most promising device technologies can then be taken from the lab to the fab into production, into development and production, benefiting the industry partners and the entire ecosystem for innovation in the US.